All right, so homework, this is homework number 7. Emily, did you mean number 4 or 40? It was 40? Oh, number 40. Oh, I see. Yeah, number 40. Okay, no problem. So let's look at number 28 first, and then we'll do number 40. All right, so number 28, it says use the laws of logarithms to expand the expression. So I want to expand expression. And my expression reads as follows. It could be different from yours in terms of the numbers, but I think the structure behind it should be the same. It's log base 3 of the square root of 3x to the 5th power divided by 1. So this is my expression. I want to expand it using the laws of logarithms. So what's the first thing I notice? I notice that when I have a quotient. So I can use the quotient rule, which gives me that log base 3 of the square root of 3x to the 5th, close parentheses, subtracted by log base 3 of y. So that's the first thing we did, right? We applied the quotient rule for logs. And then what? What's the next thing I notice? Well, this expression here, I can't really do anything any further. So I can just leave it. But there's a bit more here to unpack. So again, we're just expanding it. We're unpacking all this single logarithmic expression. And what I notice is that this is a square root. So this square root can be rewritten using using fractional exponents. So then I'm going to rewrite the inside log base 3 of 3x to the 5th power. And all of this is enclosed by parentheses being raised to the 1/2 power. Okay, and then what do I notice? I got a 1/2. I'm going to place it out in front by the power rule. So I'm applying the power rule here. So now I have a 1/2 in front, log of 3 of 3x to the 5th. So I can see why there might be some confusion. It might be because of the next few steps, due to the fact that the expression inside these parentheses is still being, you can still separate them using the product rule and the power rule. The product rule comes first. I have this multiplication, right? So then I can rewrite this as 1/2. Now just be careful. I'm gonna put some brackets around. I have log base 3 of 3 plus log base 3 of x to the 5th minus log base 3 of y. And the reason why I do this is because this 1/2 is being multiplied to this logarithmic expression. The moment I separate it, I'm still being multiplied by 1/2. And then what I could do is distribute the 1/2. But before I do that, I realized, hey, look, there's a 5 in here. I can also place this outside of the log in front by the power rule again. So I apply the power rule. So I apply the product rule first, and then I apply the product rule. And I get 1/2. Still going to have these square brackets for now. Log base 3 plus 5 log base 3 of x minus log base 3 of y. And then what do? put the 1/2 and I distribute it to everything inside. And I get 1/2 log base 3 of 3 plus 5/2 log base 3 of x minus log base 3 of y. So see him, does that make sense? Are there any questions to any step here? Is clear? Okay, great. So yes, always be careful when you have the expression in front, this a fraction or a number in front of the log, and you have to do further expansion of the log that's next to it. Just make sure you put some parentheses or square brackets around it and just continue your expansion, and then you distribute that 1/2 afterwards. Okay, great. So that's number 28. That's expanding logarithmic expressions. So now let's look at Emily suggested the last one. Yeah, the last one is an important one to know how to do because it really brings about both logarithmic and exponential equations together. So the question says, find the time required for an investment of 4,000 to grow to 9,000 at an interest rate of 7.5% per year, compounded quarterly. Round your answer to 2 decimal places. Okay, so the first thing we have to consider is the fact that we're doing compound interest, right? So this is a compound interest problem. It's not compound continuous, so we don't have to use that PERT, P-E-R-T formula. We use the first one that we discussed. So we have to discuss compound interest. And just to remind you, the formula is A equals P times parentheses 1 plus R over N raised to the N times T. So this is my formula for compound interest that I should know. Okay. Then I'm going to specify the variables that I know versus the variables that I don't know. There's only one thing that I don't know. So it says an investment is 4,000. So we know for a fact that A is 4,000. It grows to 9,000. So, pardon me, this should be P. P is the initial investment. And A is the final accumulated value. So this investment grows from a $4,000 investment to $9,000. And it says the interest rate is 7.5%. But of course, I'm not going to use 7.5%. I'm going to transform it into a decimal. I do so by moving the decimal place to the left by 2 places. So then I get my decimal version of it is 0.075. So that's the annual interest rate. Then it says the interest rate, the interest is compounded quarterly, which means that it's being done 4 times a year. So then n equals 4. So this is the compounded interest quarterly. And what we don't know, and what we're trying to figure out is time. So this is the missing piece. And if you notice, time is a variable, that is an exponent. So again, this is a scenario where the variable is in the exponent, and you're trying to figure out what that variable is in the exponent. So the only way that's possible is to apply logs somehow. Okay, so once we have that specified, let's plug in the things that we know into the equation, our formula. So you get 9,000 equals 4,000 times 1 plus r is 0.075 divided by 4 raised to the 4t. So what I'm trying to do is my goal or objective is to find or solve for value of t. That's the goal. So I want to mark my goal. Boom. Want to get that. So right now I can't get it. I need to do a certain number of algebraic steps. The first of which is I want to find what that value is for now, because I don't want to keep writing 1 plus 0.075. So this is when you can use your calculator. And let's just simplify our fraction, our expression inside the parentheses first. And I get this number here, so I'm just going to rewrite this. So I get 9,000 equals 4,000 multiplied by 1.01875 4t. So that's what the expression within the parentheses becomes. It becomes 1.01875. Okay. Okay. And so now I still want to get t. The problem is I have all of this other stuff along with it. The first thing I can do is I can divide by 4,000 on both sides. That way I can get rid of the 4,000. So then the 4,000 cancels with the 4,000. The 3 O's cancel with the 3 O's. And I get 9/4 equals 1.01875 raised to the 4t. Now, what do I do? What's the step that I do here to get the t no longer into no longer being a exponent? So what's the major step here? Well, Chen, I think you're implying this, right? Before we divide, though, I need to apply logs. So I think that's the step that you implied. So apply logs here. So I'm going to take the log of both sides here. And I'm going to take the log of both sides here. Now, do I need to use a specific base for this? I can use any base. So I'm using the common log. So base 10. I could use ln, perfectly fine here. I can use a log of base 2 or any other base that you're interested in using, but I'm just going to use log base 10. So I apply log on both sides. So I apply log on both sides. And then what happens after that? That 4t is being placed in front now because I can apply the power rule. And so then I get log of 9/4 equals 4 times t times log of 1.01875. So you see what I just accomplished? I was able to now bring that exponent 4t in front. And still, I want to get what t is. So then I need to divide again both sides by the 4 and the log. And now the 4's here cancel, the logs here cancel, and I'm left at t is equal to log of 9/4, and you probably could have written it as 2.25 as the decimal version of it. And this is being divided by 4 times log of 1.01875. And then when you place this in your calculator, you get the following. So we get log of 9 divided by 4 divided by 4 times log of 1.01875. And what I get as the approximation is 10.9134 ... And we want it in the nearest decimal places, 2 decimal places. So then I'm going to say t is equal to 10.91 years. Any questions, Emily, about this? Is this clearer now as to how to approach this problem? You understand now? Okay, great. Was there a particular part that was difficult behind this, or no? So just be mindful that whenever you have a problem like this with compound interest and you're missing or you're looking forward to the time, then you need to apply logs. Yeah, that's right, Emily. So I was literally thinking about this yesterday. It's just that the way mathematics is taught, it seems as though you understand or learn it by someone else telling you what the mathematical concept is. But actually, mathematics is not learned by seeing someone else do it. It's learned by actually you doing it. And when you say, oh, the act of doing mathematics, what does that mean? For now, I guess you can consider it as solving problems. So the more you can solve the problems, the more you do mathematics. And as you do mathematics, quote unquote, do it, you gain the understanding that way. So an essential component of understanding mathematics and getting good at it is to do lots and lots of problems. That's the idea. Okay, any other questions on homework number 7? $35. Okay, so number 35. Okay, yeah, that looks a little looks a little crazy, right? So we got 125. 125 is being raised to the x power plus 5 being raised to the 3x plus 1, and this equals 400. So some of these numbers, again, for your assignment could be a little different, but the approach and the manner in which we solve it is identical. Okay. Okay, so it says find the exact solution and then find the approximation to the solution. So again, we talk about this idea of exact versus approximate. Approximation deals with the decimal expansion of it, whereas the exact solution is exactly, without using the word exact, it's kind of hard, but it's the expression where there is no approximation. It's kind of like saying it is what it is. So when we say, for example, ln of 3, ln of 3 is exactly that value. We don't have to worry about the precision behind the approximation because that's exactly what it is. But if you want to know the approximation of it, then you plug it in your calculator then it spits you out decimals. But again, that's only an approximation. Okay, so I want to solve this equation, right? That hasn't changed. So I want to solve for x. Again, this idea of solving for x has been embedded in our brains. The issue here, though, what's the issue? The issue here is that these x's here are in two different. First of all, I want to get all the x's no longer being the exponent, but I have two exponents here. So then that's a problem. Okay, so far it looks like we have certain issues here. But there's one thing, I remember I mentioned saying this, that you need to start developing is what's called number sense, having a sense of what numbers are. And if you notice, the base of these two expressions are quite related, aren't they? 5 and 125 are connected. And how are they connected? Well, 125 is exactly 5 cubed. So then how do I know that? Well, I know some of the powers of 5s. And like I mentioned before, you should have an idea of what the powers of 2s are, the powers of 3s, powers of 4s, powers of 5s, powers of 6. You should have a list of the powers and just have an idea of what numbers are, what kind of powers. So 125, you should know, is 5 cubed. You should be able to recognize that. So once I'm able to recognize that, then I say, okay, I can rewrite 125 as 5 cubed to the x power plus 5, 3x plus 1 equals 400. Correct? And then once you have 5 cubed to the x power, what do you know about 3 in the x? You can multiply. So this is 5, 3x plus 5, 3x plus 1 equals 400. And now look what's becoming. Look what I'm starting to see. I'm starting to see these two things here are identical. I just had this plus 1 here. So who has an idea of what to do here? So again, I want to get x by itself, right? What's the problem? I still can't take out all the x's into one single position. I have them in two different places, right? Okay, 3x plus 3x plus 1 equals 400. I can't do that quite yet, Chen. The reason why is because um, I can't connect the exponents like that because of this plus sign. The only way that's possible, Chen, to add this exponent with this exponent, and this is where you have to be careful, is if this is a multiplication. When you have a multiplication of the same basis, then you add the exponents, correct? But this is a plus sign in between two exponents here. I can't do that. And even if this was a multiplication, if I add these two exponents, it doesn't give me 400. I would have to see how 400 is related to 5 and rewrite 5 using it the base of 5 and then see what the exponent would be and then make the exponents equal. So I can't do that. But look what I can try to do. I have this plus 1 here. And this plus 1 here is a little bit on the annoying side because it's just there, plus 1. Now, how can I rewrite this? A lot of this, guys, is just algebra. It's not necessarily a higher level mathematics. It's just applying your knowledge of algebra. This becomes 5, 3 to the x times 5 to the first power. This is a very crucial step to get this answer, to get the question right. Now, why? Why is this true? Because I mentioned it. If you have a sum of exponents, that means that you can also rewrite it as a product of two bases that are the same with the corresponding exponents. So if you go backwards, don't you get exactly what this is? If I were to take this, multiply it to this, don't I add the exponent? So then that's true. So I can go from this expression here to the one on the bottom. And then you might be like, okay, great. I have more fives now than before. Doesn't that not help? Well, look what happens here now. This is, again, just algebra. And look what the algebra says. I have these two common factors here. I have this and I have this. What can I do when I have two factors like this? I can factor it out. I literally can write it as 5 to the 3x, parentheses, 1 plus 5 equals 400. Do you guys see that? 1 plus 5 is what? It's 6. Look what I was able to do. I was able to go from this expression here, and now look, all the x's are in a single place because I did some algebraic steps here, and I was able to factor out a common factor, which had just one x now. I only have one x be written. I still want to solve for x. I haven't done that yet. I just rewrote the equation to make it simpler for me. And now look what I can do. I can divide by 6 on both sides. And when I divide by 6 on both sides, I get 5 raised to the 3x equals 400 divided by 6. If you did 400 divided by 6, if you divide the top by 2 and the bottom by 2, I get 200 over 3. But I still want to get x. So then what should I do to get x, guys? How do I make the x no longer a exponent? What do I do on both sides of the equation? Apply log. Right. I can apply, and again, I can apply any log base. So for now, let me just apply ln, base e. Okay. So now when I did that, now look what I have. I have an exponent inside a logarithmic function, and I can place it outside using the power rule. And then I get 3x times ln of 5 equals ln of 200 over 3. And again, I have this x here. Now what can I do? I can divide both sides by 3 times ln of 5 and 3 times ln of 5. And then x is equal to ln of 200 over 3 divided by 3 times ln of 5. And this here is my exact solution. It's exactly what it should be. And then when I plug it in my calculator, and I think they want it to nearest decimal places, if I were to plug it in, I get 0.869808. Okay. Any questions about this? I think what might be a bit troublesome is this intermediate steps here. Okay, so just be very careful. Have your eyes peeled to know or to see where you're headed with the equation. Again, the overall goal is to find x. The problem is that x is in two different terms. So to find a way, algebraically speaking, to get those terms together with the x's being in the same place. And it just so happened that it worked out because the 5 to the 3x here appears twice. I can rewrite this expression here as 5 to 3x times 5, and then I can factor this out. I can factor out. So I'm using factoring again. That technique is essential for mathematics. And then I just go on my way now from here to divide by 6, then apply ln on both sides, and then solve for x. Okay? All right, so any other questions from this assignment? Everything okay? All right. Okay, great. So guys, we've done a lot so far. We've covered quite a number of functions over the past several weeks, over the past 15 or 16 lectures. Again, we've done what functions. We've talked from the very beginning. We've talked about functions and what they are as a general idea. And then we went into composition of functions, how we compose two functions with one another. We talked about inverse functions, and then we talked about quadratic functions, we talked about polynomial functions, we talked about exponential functions, and we talked about logarithmic functions. And like I said in the beginning of the semester, that's all we're going to be talking about. Functions, functions, and more functions. So now we've reached the moment in our trajectory that where we're going to be considering the last kind of function and for the semester. And these functions are under the umbrella of trigonometric functions. So from this point on to the end of the semester, we're strictly going to be talking about trig. That could be a good thing for some, or that could be like a concern for others. Because I know trig does give some trouble to students in the past. But I hope to dispel any issues that you may have with trig. And trig is one of the most important aspects of mathematics, even for those students who don't pursue mathematics. Trig is found in and so useful in many facets of our life. And it has everything to do with angles. And there's a lot of aspects of our lives that revolve around knowing angles and how to see connections among angles. So this is going to be the last topic that will be covered on exam number 2. And it's trig, but we're going to talk about the fundamentals of trig. Okay, we're not going to get into any advanced topics as of now. And again, on Wednesday, we're going to have a review session. So I plan to upload the review sheet later today. So you guys have some time to look it over, and then we'll go over it on Wednesday. And again, you have tutoring. You have the tutoring option available for those who need it through Zoom. Okay, so we're going to talk about the fundamentals of trig. Trigonometry. So how do we start? There's so many ways to start this. One way is to start by saying, where are we going to be? Where's our setting, right, for this whole scenario? Where will we be? We will be in the XY plane. So our typical XY plane. But now we're not just going to consider it as X and Y anymore. We're going to be considering it with angles. So the first thing is we're going to be considering the positive x-axis. So this portion here, this portion here of the graph, we're going to be considering it as 0 degrees. Okay, so one major thing is about degrees, right? And I think most of us understand the following, that if you go around the circle, how many degrees is one full circle? Does anybody know? I think most of us have heard this before, right? So if you go around the circle, how many degrees is that? 360, right? So everybody says 360. Very good. And that's true. But the question that many people don't know how to answer is my question of why. Why is a circle 360 degrees? And so that's when people are like, wait, what? So we know this to be true, but we don't know really why. Or do you? Does anybody know why it's 360 degrees? So Chen says, because one quadrant is 90. So then my question is, how do you know that one quadrant is 90? Exactly. That's the reason. Because someone told you. And then you said, yes, this must be true. And you just went with it. But there has to be a good reason why. Or there has to be some reason as to why that's true. Well, see, this is where it is a right angle, Andrew, but then how do you know that right angles have 90 degrees to them? How do you know that? So what I'm trying to do to you guys is to make you guys, when we use tools to measure, yes, but who created those tools? You understand? I'm trying to get to the essence of what a degree is. What is 1 degree? So you tell me, yeah, use a protractor, but then I'm like, who created the protractor? Who said that, yeah, this is gonna be 90? Yeah, the right angle is gonna be 90, this is gonna be 180, and I'm gonna separate this into 180 degrees. Who came up with that? You see, there's a lot of things that we take for granted. And so I'm trying to just to like, jolt that mind of yours to think why things are true. So the problem with this is that mathematics is taught in such a way that people just consume it and just memorize things to be true. But the reason for why it's true is completely lost. And so then, and if that's the case, then a lot of understanding is lost because it's just really recall and memorization, whereas mathematics is much more than that. And an essential part of mathematics is the history of it. So you have to know your history. That's why you take history, European history, all these different kinds of histories. It's actually important. And there's a lot of history embedded in mathematics. Or I should say there's a lot of mathematics embedded in history. So this idea of 360 degrees is actually an arbitrary reason. There is no real good reason. Well, I shouldn't say that, but there's nothing special about 360 that makes that necessarily a characteristic, an intrinsic characteristic of circles. Someone said back in the day, and this is back in the Babylonian time, okay, we're talking about the ancient civilizations. Babylonians is one of those, um, very much studied civilizations. And a lot of the mathematics, at least the elementary mathematics that we know of, came from that time period. In particular, this idea of 360 degrees being considered one revolution around the circle. And the reason why they chose 360 was because 360 is very nicely divisible by a lot of numbers. That's the reason why. So like 2, 3, 4, 5, 6, 10, 12, all these numbers divide 360 very nicely. So someone decided, I don't know necessarily what person or what individual, but back then in the Babylonian era, they decided that 360 would represent 360, a full revolution around the circle. And so that's why everything else follows. Also, if it's 360 degrees around the circle, then that means that half of it would be what? 180 degrees. And then you say, oh yeah, so then that means that half of that would be what? 90 degrees. So one quadrant is 90. According now everything starts to fit through, but someone had to say it. You understand? So then this is 90 degrees. Another 90, that would be 180 degrees. Another 90 would be what? 270 degrees. And so on and so forth. And we're going to be moving in the what's called the counterclockwise direction. So if I go in the opposite direction of how clocks normally go, right? If I go in the opposite direction, I'm going to have a positive number to it, associated. So if I go around, the angles are all positive. And again, this here can be considered like my my starting position, 0 degrees. So as I start to move, my angle measurements, and what am I really measuring? I'm measuring what's called the angle that's made with the terminal side. So again, there's going to be a lot of terminology here. So this is called the terminal side. The terminal side makes a certain angle, right? It makes a certain angle between this side, which is just a ray. This is a ray from the origin. And again, the origin is the 0 by 0, 0, 0 point here. So it's a ray that comes from the origin, and that ray, which is a point, and then the other, it's a point where there's one direction of the line. And this angle here, we're going to call it, normally we're going to use the word, the symbol theta. This is a Greek symbol. So again, a lot of Greek influence is embedded in mathematics. So we have the theta. So theta here is a Greek symbol, is a Greek letter. And oftentimes we use theta to represent an angle. Represents an angle. Okay? So we're measuring this. We're measuring the angle made between the terminal side and the positive x-axis, or the 0 degree line. So as we move around, right, our angles here grow. It increases. So this is one angle, and let me just write another angle here. So if I have an angle like this, then the angle that I'm considering is this angle here. You see? This is another theta. I'm going to call it theta. So this is theta 2. And this is theta 1. Okay? So this angle would be some angle bigger than 180 degrees, but smaller than 270 degrees. So then we start talking about quadrants. So again, this is what? This is quadrant 1. And I move around in a counterclockwise direction fashion. So this will be called quadrant 2. This will be quadrant 3. This will be quadrant 4. Any questions about this? Any questions about degrees? Any questions about how this XY plane now, this Cartesian plane, is now being utilized to explain angles? Is this clear to everybody so far? Okay. I guess so. All right. So this is the beginning of it, of trig. So now that we have this, let's talk about something that's called coterminal angles. So what are coterminal angles? So they're angles. They are angles that are associated with the same terminal side. So an example, if I have another XY plane here, again, this is 0 degrees, this is 90, and I were to have a terminal side somewhere in the first quadrant, and I'm going to say that this angle here is 50 degrees. So I went 50 degrees in the counterclockwise direction from 0 degrees. So this is 50 degrees. All right. Now my question is, what's a coterminal angle to this 50 degrees? What would be another angle associated to this terminal side? So to find the coterminal angle is actually not much work to it. And what I'm going to say is that there's actually many, right? And Daniel Guild, I think he's onto something. How did you get 410? What did you do to get 410? You added by 360. Very good. So 360, what does it mean again? If you add 360, if you go around 360 degrees, you move in a full revolution around. So if you tell me I went 50 degrees counterclockwise and then I added another 360 degrees, I come right back. So then this angle here, you see that? This angle here is this. This angle here is 410 degrees because I took 50 and I added 360 to it. So 410 degrees represents one full revolution plus another 50 degrees. So what are the coterminal angles? 410 is one of them. What's another one? Can't I add another 360 degrees again? So if I add another 360 degrees again, what would I get? If I move around, and then I move another 360 degrees, where would I be? What would be this angle? So 360 plus 360, 720, plus another 50 would be what? 770. And as you can tell, I can add 360 again and again and again. I would get another angle that shares the same terminal side as 50 degrees. So that's the confusing part behind trig, is that there's so many angles that refer to the same position. So in a sense, there's an ambiguity with all of these different angles that represent the same position in the XY plane. But that's why we discuss it first, because we have to understand that 410 degrees, 770 degrees, 50 degrees, in a sense, they're the same. In a sense, they're different because you move around the XY plane more than once for several of those. But where you end up is exactly the same place. Where you end up for 50 degrees will be the same thing where you end up for 410 degrees, 770 degrees. And you can also go backwards as well. Instead of going in the counterclockwise direction, what if you goes in the clockwise direction? That's something I should mention. If you go in the clockwise direction, then actually my angles here become negative. So 0 degrees, right? If I go around here, 90 degrees, 180 degrees, 270 degrees, and finally 360 degrees when I go one full revolution around. What if I go the other direction? If I go in the other direction, this actually equals negative 90 degrees. And this will be equal to negative 180 degrees. This will be equal to negative 270 degrees. Do you see that? If I go in the clockwise direction, my angles are all quote unquote negative. So this would indicate that if I go in this positive direction, I get some positive angle. And if I add 360 to that angle, I'll get the same angle associated with the terminal side. But if I want to go in the opposite direction, then I would have to subtract by 50 of 360. So I have to subtract 50 by 360. So what does that give me when I get 50 minus 360? So 50 minus 360 is negative 310 degrees. So all of these angles here, guys, all of them, these are coterminal angles to what angle? To 50 degrees. And again, I can subtract 360 again, and subtract another 360 to get more coterminal angles. There's an infinite number of coterminal angles. Okay. Any questions about that coterminal angles? Again, you literally just add by 360 several times or more than once, or you subtract by 360 more than once to get next coterminal angle. Okay. Okay, so we're getting to the basics of it, right? Now, there's one thing we have to make clear from the beginning. There's going to be a lot of duality between the angle measurement. So we're so accustomed, or we have been so accustomed to using degrees to represent angles. But there's another measurement that we need to know. And that other measurement for angles will actually prove to be more useful than degrees. And that's the idea behind radians. So radians is an alternative angle measure. And it's actually much more, it's not an arbitrary measurement as degrees are. Radians is actually specifically attributed to circles. So the idea comes from the following. The idea comes from, and we're going to discuss this much more in detail, but for now, I'm just going to introduce this idea of the unit circle. Okay, the unit circle. So it's amazing to talk about trig, and you're going to be talking about right angles and right triangles. And it's interesting to see how right triangles, to understand trigonometry and right angles and triangles, you need to understand circles. So there's a connection between triangles and circles here. So the unit circle is a circle that has a radius equal to 1, and the center is at 0, 0. That's what the unit circle is. So take the unit circle, and the radius is 1. If you guys remember, what's the formula for the circumference of a circle? Again, this is back to your middle school days. What is the circumference of a circle? And again, the word circumference just means perimeter, right? We're looking at the perimeter of a circle. So if I go around the circle, the length of it tells me the circumference. And for those of you who don't remember, The circumference is what? 2 pi times the radius, right? That's one of the formulas. So what would be the circumference of a unit circle? Well, if the radius is 1, the circumference would be 2 pi. What does that mean? That means that if I move around the circle, if the length of this, if I move it around once, right? If I go around it once, it's exactly 2 pi. So that's exactly what we're going to make now. We're going to say that 2 pi radians is equal to 360 degrees. This is my conversion. My conversion between 2 pi, my conversion between radians and degrees. And I'll take one step further and divide. I'm going to divide both sides by 2. So in reality, this is the one that normally people use. Pi radians, whatever that means, right, is equivalent to 180 degrees. So this is my conversion. This is an essential conversion. For every 180 degrees of an angle, I have pi radians. And pi, again, is using the same number that we know for pi, 3.1415926. So an alternative way to represent the xy plane now no longer utilizes degrees. Instead, we're going to use radians. So we're going to use rad for abbreviation. So 0, right? This will now be what? This will be what? Pi rad, right? Pi radians. But what's half of pi? Or I should say, what's half of 180? Isn't it 90? So half of pi is really just half of pi. So this will be considered as pi over 2 radians. You start to see that? And then slowly but surely, this is pi over 2, this is pi over 2, this is pi over 2. Then how many pi over 2s do I have if I go from here all the way to here? It will be a total of 3 pi over 2. So this is the place where students start to like kind of lose their footing a bit because of the conversion to a different angle measurement. Again, I think most of you are used to degrees, but radians is actually the more important measure eventually as you continue to know how to deal with. Why didn't we use r in the circumference equation? Well, the reason we didn't, well, we did use it. It's just that when you plug in 1 for r, right, it's 1. So 2 pi times 1 is just itself, 2 pi. So in a sense, it seems as though we didn't use it, but we did. And it's because the radius is 1. Make sense? So that 1 makes it, in a sense, like disappear. In a sense. We don't see it anymore. And again, I brought this up because I wanted to find the circumference of the unit circle. And then I realized the circumference of the unit circle is 2 pi. And I wanted to connect make the connection between 2 pi, which is the length around a circle, and 360 degrees. And somebody decided to make this a conversion. 2 pi rad equals 360. And so therefore now pi radians is 180. And because I have this conversion between degrees and radians, I can create a new way to see or to represent angles. This is a new way, a different way. So for example, pi radians is the same thing as saying 180 degrees. It's the same. Because of that, then pi over 2 radians means represents 90 degrees. 3 pi over 2 radians represents 270 degrees. If I go all the way around, that's 2 pi radians, which is equal to 360 degrees. Okay, so then what do I know? I know pi over 2 radians equals 90 degrees. 3 pi over 2 radians equals 270 degrees, and so on and so forth. Okay? Okay. So then how do we go from degrees to radians, radians to degrees? So if I want to convert degrees to radians, actually, let's go from radians to degrees first. From radians to degrees. What do I do? So for example, if I have something that's called pi over 6, right? How do I interpret pi over 6 as degrees? Well, I have to multiply by a certain factor. And I multiply by 180 over pi. That's what I multiply by. So I multiply by 180 over pi. Now, why do I do that again? Well, because, remember, I mentioned pi radians is 180 degrees. So this will be the conversion factor, 180 over pi. And then look what happens when I multiply it this way. The pi's here, they cancel, becomes 1. And 180 divided by 6 is 30 degrees. So pi over 6 radians equals 30 degrees. Give me anything in radians and I can convert it to degrees by multiplying by 1 over pi. And if I want to go in the opposite direction, if I want to convert degrees to radians, then I have to do multiply by the reciprocal. So multiply by pi over 180. So an example, what if I want to write 135 degrees? And I have 135 degrees, and I want to write it as an expression in radians. So what I do is I multiply by pi over 180 degrees. And that will result in 135 pi divided by 180. But of course, I'm not going to leave it that way. I can cancel, or I can reduce that fraction, 135 over 180. Maybe it's not apparent, but you can divide by 45 degrees. And if I divide by 45 degrees, I get 3 pi over 4. So 135 degrees is equivalent to 3 pi over 4 radians. So one thing I want you guys to see is that I can divide up my XY plane in various ways, and at least for now, you should know we should have 3 different ways to divide up our XY plane. So one of them being is when everything's divided into fourths. So if I got pi and I got pi over 2, I can divide this in half again. I can divide pi over 2 by 2 and I get pi over 4. This is pi over 4. Again, this is 0. So then I divide this into a fourth, right? I divide this fourth into another half. So I have pi over 4. This is pi over 4. Then this would be what? Another pi over 4, which is 2 pi over 4, which is pi over 2. And then I have another one, right? I divide this again. So think of it like a pizza pie. And this is dividing into slices. And this is 3 pi over 4. And then pi would be what? 4 pi over 4, but that becomes just pi. Then I divide this here in half. I just extend this line here. Of course, my lines are not that straight. Then this becomes what? 5 pi over 4. Do you guys see the drift behind this? This is 2 pi over 4. So this is 1 pi over 4, one slice. 2 pi over 4, second slice. 3 pi over 4, 4 pi over 4, 5 pi over 4. This becomes what? 6 pi over 4. And then divide it again. 7 pi over 4. And then finally, when you get back to the other side, it's going to be what? 8 pi over 4, which equals 2 pi. Does that make sense? Oops. So this is one way to divide up our xy plane into pi over 4s. So this is when xy plane is divided into pi over 4. Pi over 4s. But then there's another way to divide up the xy plane. And the xy plane is divided into pi over 6s. Now, what is that? And again, I can rewrite this using degrees. So pi over 4 is what? Pi over 4 is actually, again, if I want to rewrite pi radians into degrees, multiply by 180 over 4, 180 over pi. So if I do pi over 4, multiply by 180 over pi, the pi's cancel. I'm left with 180 over 4. That gives me 45 degrees. So this is 45 degrees. And then this is going to be what? 90 degrees. This is going to be what? 135 degrees. This is going to be what? 180 degrees. This is going to be what? Another 45 degrees. This is 225 degrees. And this is going to be what? 270 degrees. And this will be what? 315 degrees. And this will be finally 360 degrees. Do you see that? That's another way to represent. So 45 degrees. And now I'm going to divide it up into pi over 6s, which is approximately, it's not approximately, it's exactly the same thing as what? Pi over 6. If you do the same thing, pi over 6, multiply by 180 over pi, the pi's cancel. I'm left with 180 over 6, which equals 30 degrees. So pi over 6 is the same thing saying 30 degrees. So I'm going to divide up my pi. Oops. I'm going to divide up my pi into pi over 6s. So take pi, right? Remember, pi is this. Pi is only this upper half. Take pi, so think of it as the top half of a pizza pie, and divide it into 6s. Okay, what is that going to look like? So this will be what? This will be the first pi over 6. So this would be pi over 6. This would be 2 pi over 6. This would be 3 pi over 6. This would be 4 pi over 6. This would be 5 pi over 6. This would be 6 pi over 6. Then this would be 7 pi over 6. Then this would be 8 pi over 6, this would be 9 pi over 6, which is 3 pi over 2. Then this would be 10 pi over 6, 11 pi over 6, finally 12 pi over 6, which is the same thing as saying 2 pi. You guys see this now? Do you guys see how I'm dividing this up? And pi over 6 again can be rewritten as what? 30 degrees. This would be written as what? 60 degrees. This is what? 90 degrees. Then this is what? 120 degrees. This is going to be what? 150 degrees. Then this is 180 degrees. You see this consistency behind all of this? This is 210 degrees. This is going to be 240 degrees. This is going to be 270 degrees. This is going to be 300 degrees. This is going to be 330 degrees. Any questions about this? How we're dividing up our XY plane? So you have to make these connections. Pi over 6, 30 degrees. Pi over 4, 45 degrees. And there's one more. There's one more that we normally do. Is the XY plane divided into pi over 3. So what if I have pi over 3s? So again, think about pi, okay, from 0 to pi. And instead of now having just pi being divided up into 4s or divided into 6s, I'm dividing into thirds. So I'm dividing pi into thirds. Pi is 180 degrees. So if I divide pi into thirds, it becomes 60 degrees. So there's a lot of relation or overlap with this schematic diagram there. So this is really what? Pi over 3 divided into thirds, right? So let me use a different color here. So this is pi. Might be a little too faint, right? Yeah, let me just use the pink. This is pi over 3. Then the next slice would be 2 pi over 3. Then the third slice would be 3 pi over 3, which is just pi. Then this would be 4 pi over 3. Then this would be 5 pi over 3. And then finally 6 pi over 3, which just gives me 2 pi. And pi over 3, the same thing as saying 60 degrees. If you have another 60 degrees, you get 120 degrees, which is exactly the same thing that I get here. You see? 60 and 120. And then you get another 60, that'll be 180. Then add another 60 and you get 240, which is exactly what pops up over here. And then you get another 60 degrees would be 300. And you get back to 360 degrees. Okay. Any questions about this? Any comments? Any clarification behind radians and how we divide up our XY plane with these different radian measurements? Okay. All right. So now that we have a better understanding of this, let's do the following. So I want to find a coterminal angle that is between 0 degrees and 360 degrees. So an example, if I have 400 degrees as my angle theta, I want to find another coterminal angle to this. This will be on our test. Yeah, this is going to be the last topic on your test. And again, it's not going to be any more complex than what this stuff is right now. I'm sure it gets much more complicated, and we'll do that after our second exam. But the fundamentals of it, which is uh, um, degrees to radians, radians to degrees, coterminal angles. Yeah, I think that's the extent of it. It's not going to be anything more than that. And reference angles. We're going to talk about reference angles. But let's do this first. What is the angle or the coterminal angle to 400 degrees? That is between 0 and 360. So remember what we talked about coterminal angles? You just have to add by 360 as many times as you like, or subtract by 360 as many times as you like. Well, 400 degrees is outside or above 360, right? It's greater than 360. So it would mean that to get the coterminal angle that I'm interested in between this interval, it would mean that I would have to subtract by 360. So if I subtract by 360, I get 40 degrees. And that will be the coterminal angle, 40 degrees. So we have to be mindful of what interval you're in. So let me give you another example. So what if my angle is 780 degrees, for example, and I want to find a coterminal angle. And again, my coterminal angle, I just specified it to be between 0 and 360. Like I said, there's an infinite number of coterminal angles. So in order to get a specific one, I need to create this interval here. So to go from 780 degrees to an angle that's coterminal to it in the 0 to 360 degree range, I have to do what? I have to subtract by 360, don't I? And when I subtract by 360, I get what? 420 degrees? Yeah, it'll be 420, but 420 degrees is not in the specified interval that I'm in, that I want. Right. So you have to repeat again. So subtract by 360 once more because that will give you the next one, right? And if I do so, what do I get? I get 60 degrees. So the coterminal angle that I'm interested in is 60 degrees. So 60 degrees and 780 degrees are coterminal to one another. Does that make sense? Okay. What if my angle is, for example, negative 800 degrees? What would be the coterminal angle in this case? Or what would this entail if I have a negative 800 degree angle? Remember, negative means I'm just going in the clockwise direction. But I want my coterminal angle to be between 0 and 360. And that's right, I need to add this time, right? I need to go in the positive direction, so I must add by 360. So if I add by 360, what do I get? So if I add by 360, I get 400 and negative 440. But this number is still not between 0 and 360, so I must add again, right? I must add by 360. If I add by 360, what do I get here? I get negative 80. but that's still not between 0 and 360 degrees. So I need to add by 360 once more, right? And then Felipe says the third try is going to give us 280. And that would be exactly what I want, right? I want an angle that's coterminal to negative 800, but between 0 and 360. That would be 280. Makes sense. So this idea of coterminal angles, I'm either adding multiple times by 360 or subtracting multiple times by 360. And again, all these angles are coterminal. Okay, great. So that's one thing. And now I want to find a coterminal angle. Oops. Coterminal that is between 0 degrees, no, sorry, 0 and 2 pi radians. So remember, we can do, if we could do it to degrees, then we can do it to radians as well. So let me give you a angle in radians. So again, this might be the more difficult part, right? Because we're dealing with radians, and degrees is more intuitive for us because we're used to it. But we have to get used to radians as well. And again, to deal with degrees and to find a coterminal angle, you need to add by 360 or subtract by 360. It could be more than once, right? But what is 360 in radians? It's 2 pi. So we should be able to add or subtract by 2 pi to get the next coterminal angle. And my coterminal angle, I want it to be between 0 and 2 pi. That's one thing I could do, right? And let me just copy this again. Because this will prove to be very helpful in scenarios such as this. Let me resize this. Okay, so I want to find an angle that's coterminal to 19 pi over 6. And I already know how this kind of divides it up, right? So this is pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8, 9, 10, 11, then 12 pi over 6. Then I move it, I continue moving in the counterclockwise direction. If I move around once and then I continue again, this will be now what? 13 pi over 6. And then this will be what? 14 pi over 6. 15 pi over 6. 16 pi over 6. 17 pi over 6. 18 pi over 6. 19 pi over 6. So 19 pi over 6 is coterminal to 7 pi over 6. I could also find that out. Let me just write this as theta. So theta is equal to 19 pi over 6. I could also find the coterminal angle by subtracting taking 19 pi over 6, subtracting by 2 pi. Which is the same thing as saying 19 pi over 6, subtracted by 12 pi over 6. 19 pi minus 12 pi is 7 pi over 6. And this is inside the intervals, 0 and 2 pi. So having this schematic here in your head and seeing how these angles repeat themselves as you go around helps you in finding the coterminal angle. It will help you. So again, we can add and subtract by 2 pi, or you can visualize this And I think visualizing might help much more, especially when we deal with radians. Because of the fractions, I think that might be the problem. The fractions might mess people up. So I'll give you another one like this. So what if my angle here is 17 pi over 6, 17 pi over 4? And I want to find the coterminal angle to this. So I'm going to use that pi over 4 diagram that we had. And I'm going to do this very similar thing that I just did in the previous example, right? This is 0, this is 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, and then I come back as 8 pi over 4. But if I continue moving around after I do that one complete revolution, if I continue going for the second one, what will this become now? So this is 8 pi, this will be what? 9 pi. Do you see how we repeat it now? 9 pi, 10 pi over 4, 11 pi over 4, 12 pi over 4, 13 pi over 4, 14 pi over 4, 15 pi over 4, 16 pi over 4. Do you guys see that? So if I go around 2 full revolutions, this will be 16 pi over 4. Wait, is it 16 pi over 4? Yeah, it is 16 pi over 4. It is 16 pi over 4, which becomes just 4 pi. And then 16 pi over 4, 17 pi over 4, 18 pi over 4, 19 pi over 4. Oh, I already went a little too much. This should be it. 11 pi over 4 is just equal to, this is the same thing as saying 17 pi over 4. So in this case, I had to subtract 17 pi over 4 by 2 pi and then by another 2 pi. So if you notice that 17 pi over 4, I can subtract this by 8 pi over 4, which is the same thing as 2 pi over 4, and then I get 9 pi over 4. But 9 pi over 4 is more than 2 pi. So I subtract by 8 pi over 4 again, and I get pi over 4. So looking at the diagram that we had set up before makes finding coterminal angles much simpler, much simpler. Okay. Any questions about this, guys? It's okay if you have, if you don't, if something's unclear or if you need more clarification on, particularly with radians. I think radians is an issue for some to get familiar with it. But the more we use it, the more you start to see that it's really just another way to represent angles. It'll become much more easy to deal with. Okay, makes sense? Okay, so what if my angle here is negative 5 pi over 3? Could someone tell me how to find the coterminal angle? And again, this coterminal angle, I want it to be between 0 and 2 pi radians. So how do we approach this one? So again, I would suggest using the pi over 3. That little diagram that we had. But first, we should try to figure out where is negative 5 pi over 3. Can someone tell me where is negative 5 pi over 3? What quadrant is negative 5 pi over 3 in? And again, using this might help as well. Using this diagram might help or will help. So see him says, I'm in quadrant 4. Be careful. It says negative 5 pi over 4, not 5 pi, pardon me, negative 5 pi over 3, not positive 5 pi over 3. So you would be correct if 5 pi over 3 is in the 4th quadrant, but I'm talking about the negative one. So how would this diagram here change, or how would we modify it so that we have negatives as well? So remember, when we go in the counterclockwise direction, this is a positive angle. So all these angles are positive because I'm considering the counterclockwise direction. But remember, negative means clockwise direction. So instead of cutting it from here and saying that's 1, that's 2, that's 3, that's 4, that's 5, I'm going to cut it in the other direction. Say this is 1. But this would be what? Negative pi over 3. And then this would be what? Negative 2 pi over 3. And then this would be what? Negative 3 pi over 3, which equals what? Negative pi. We already knew that. And then this would be what? Negative 4 pi over 3. And then this would be what? Negative 5 pi over 3. So negative 5 pi over 3 isn't actually in the first quadrant, quadrant 1. And the angle that's coterminal to it is going to be pi over 3. So pi over 3 and negative 5 pi over 3 are coterminal angles. One of them just deals with this angle here. That's pi over 3. The other one deals with this angle here. Negative 5 pi over 3. So does everybody follow that? Then maybe draw that. That might help. So if I go from here to here, this is negative 5 pi over 3. But if I go from here to here, this is simply pi over 3. And do you see? They are exactly coterminal because they share the same terminal side. Make sense? Is this becoming much more understood? It may take some time. So we did set with negative 5 pi over 3. Okay. Okay, how about another one here? What if my angle here is 25 pi? And I want to find the coterminal angle to this. And I want this angle to be between 0 and 2 pi. So where is 25 pi? How do we figure that out? Does anybody know where is 25 pi? No. So remember, we start with 0, right? And this becomes what? This becomes pi. And then when you come back one full circle, this is 2 pi. And then if you continue, this would be what? 3 pi. And then you go around 2 full revolutions, this becomes 4 pi. Do you see that? This is 5 pi. Then this is 6 pi. These are all coterminal angles. 2 pi, 4 pi, 6 pi. Pi, 3 pi, 5 pi. These are all coterminal. So all of the even multiples of pi are on the right positive x-axis. All the odd multiple multiples of pi are on the negative x-axis. So eventually what's gonna appear? Eventually negative 25, pardon me. Eventually 25 pi is gonna appear. So that's after I do what? Probably around, if I do 6 revolutions around, that will be 12 pi, right? That's right. If I do 12, so I have to do 12 revolutions. If I move around the circle 12 times, I will get to 24 pi. And then one more halfway revolution would equal 25 pi. So what's going to be the coterminal angle to 25 pi? What's going to be pi? All right. So any questions about coterminal angles? Can you repeat that? Oh, so, okay. So again, we started with 25 pi, right? The angle is 25 pi. And first we have to understand where is the angle that they give us? Where is it in the XY plane? We know for a fact that this side here, this x-axis here, is 0 degrees. This is where we started, right? And then when we go halfway, this becomes pi. And then when I make one full revolution, this becomes 2 pi. So 0 and 2 pi radians are coterminal with one another. Then if I go around 2 pi and then another halfway around, I'll get to 3 pi. And then if I do 2 full revolutions, I get to 4 pi. And so on and so forth. 5 pi, 6 pi, 7 pi, 8 pi, 9 pi, 10 pi. So all of the positive multiple, even multiples of pi's are on the x-axis to the right. Then all the odd integer multiples of pi are on the left side of the x-axis, which would mean that 25 pi will eventually, if you go around 12 and a half times the circle, if you go around 12.5 revolutions around, starting from 0, I reach 25 pi. So 25 pi represents 12 and a half revolutions around the xy plane. And therefore the coterminal angle to 25 pi is pi. Does that make sense? Remember what coterminal means? It just means that it's an angle that represents the same terminal side. So if I go around the circle 12 times, right? If I do it 12 times, this would be 25 pi. But I just want to find another angle that represents that same terminal side. And that's pretty simple. It's just pi. It represents the same terminal side. It's just that one of them, you have to go around the xy plane 12 and a half times, whereas the pi, you do it half. You do half a revolution around to get to pi. But again, it's the same terminal side. Eventually, this idea of coterminal becomes just part of our life from now on. At first, it may seem annoying or maybe not unclear, or as to maybe you don't see the purpose of having to repeat a specific angle like in other with other numbers. How is one side a terminal side represented by different angles at the same time? It just seems to be a bit redundant or a bit confusing, but this is part of the nature of trig. There's a redundancy, there's an ambiguity with these angles. So we have to always be careful with an angle because there's an infinite number of ways to represent the same angle. And that's the, I would say, the strangeness behind trig. But once you understand that, once you clarify that part, then the rest of trig doesn't become that complex, even though there is more advanced concepts coming up. But this is very important to establish in the beginning, coterminal angles. And then we'll talk about reference angles and build from there. So your exam will just include up until here, nothing else, nothing further. So you need to know degrees to radians, radians to degrees, how to convert from one to the other, and this idea of coterminal angles, and that's it. So don't fret too much about that. Okay, so I'll stop here. If you have any questions, let me know. If not, then please, for those of you who need it, would benefit from it, check out the link that I gave in the email about